Hello, welcome back to Chemical Engineering Statistics. This segment discusses the population mean confidence interval as one of the most popular methods in inferential statistics. From our discussion about population versus sample, we cannot be certain of the true value of a population parameters, but simply need to estimate it. In the previous segment, I introduced the point estimate, which is how to express the value of these population parameters with single numbers. Well, here we are discussing another way stating the population parameters as a confidence interval, which is a range of random variables values that are believed to contain the true value of the population parameter. The confidence interval is always calculated at the confidence level or significance level that was set before the calculation. By using a confidence interval, the population parameter estimations become more reliable. A narrower interval implies lower estimation uncertainty, or in other words, higher precision. The confidence interval can be calculated for all population parameters, mean, variance, standard deviation, and so on. This segment of the video focuses on confidence interval for population means. In calculating the confidence interval, there are no strict rules about what confidence level values should be used. But the common practice is to use 90, 95, or 99%. Roughly speaking, the confidence level can be viewed as the probability of obtaining the true value of the population parameter. The figure on the right illustrates the interpretation of the mean confidence interval. Suppose we randomly take 100 samples of uniform size n from a population. Then we calculate the mean value of each sample, so that the mean value of each sample is obtained. The mean of each sample is then used to estimate the confidence interval for the population mean. So we get 100 intervals of confidence. Now, if we calculating the confidence intervals at a 95% confidence level, then we can expect 95 of the 100 confidence interval will contain the true value of the population mean, while the remaining 5 will not. Please note that, however, we cannot be sure which intervals contain the true value of the population mean and which do not. The confidence level reflects opportunity, not certainty. There are several cases of calculating the mean confidence interval. Here's how to calculate the population mean confidence interval if the population standard deviation is assumed to be known, or if the sample is large. In example, the sample size is more than 30. The calculation uses the random variable z, which is determined by the chosen significance level. This is the formula for that confidence interval. Note that the confidence interval is expressed as the plus-minus population mean of a term called the sample error. So this interval is symmetrical around the sample mean. Note that the sample error is determined by the standard deviation of the population, the size of the sample, and the value of z. The higher the confidence level or the lower the significance level, the z-value associated with that significance level will increase. You can conclude from the formula that increasing the confidence level increases the sample error and widening the confidence interval. For large samples, if the population standard deviation is unknown, then the sample standard deviation is considered to replace it in the confidence interval formula. The next case is if the population standard deviation is unknown and please note and the sample size is small. If the corresponding random variables can be considered normally distributed, then the confidence interval formula changes to something like this. This formula is very similar to the previous one, but the quantity of z is now replaced by t, whose value is determined by the significance level and also the degree of freedom. In addition, the sample standard deviation is used to replace the population standard deviation. Now, how to find the value of the random variable t? We can use a table. Here is a table of the t distributions, also known as the student's t distributions. The first column on the left shows the degree of freedom of the distributions, while the first row above shows the probability value or the significance level. The numbers in the body of the table represent the random quantity t. The figure on the top of the table shows that the probability is calculated as the area under the curve. For example, how to use this table? Now, what is the t-value for the calculation of the confidence interval at 5% significance level? And the sample size is 10. Okay? Now from the table, we can find the t-value at the one-sided probability value half of the significance level, or 0.025. That's half of the 5%. And we have the degree of freedom n minus 1 equal to 9. Thus, we can obtain the t-value of 2.262. I close the video lecture segment by presenting three statistics science figures who are closely related to inferential statistics. Abraham de Moivre is noted to have initiated the normal distributions. De Moivre's ideas were later continued and clarified by Carl Gauss, so that the normal distribution is often referred to as the Gauss distribution. Next, we have William Gosset, who was the statistician working at the Guinness Brewery in Ireland. He developed the concept of inferential statistics using small sample and discovered the very important t-distributions in statistics.